Circuitry is a great thing to learn, as it can come in handy from time to time. Whether it may be just a hobby, or plans to create a do-it-yourself project, this tutorial should brief you on the basics of circuitry. Just a gentle reminder that this tutorial is solely for small-scale circuits and components, the kind of scenarios you would find when dealing with Arduino programs and breadboards. Here is a table of contents for the video. Feel free to click on an annotation that corresponds to the topic you're interested in. If this is your first time learning about circuitry, I highly recommend watching the video in order. So here I have some classic parts that you'll usually find when working with circuitry. Here we have a breadboard, a battery and its backpack add-on, an LED, speaker, a simple button, a resistor, two different kinds of microcontrollers, an AC-DC adapter, jumper cables, USB to Type B, and USB to Mini. I'll cover each of these parts within this video. To start off our components list, we'll talk about jumper cables and wires, which are used to connect the components of a circuit together. So in front of us, we have a selection of jumper cables that you'll typically find in a builder kit. These wires are optimal when working with breadboards, as the tiny metal barb at the end of them works as a reliable connection to the breadboard. Regular wires are made of strands of copper which could unwind and tangle if used multiple times on a breadboard. By using metal barbs, the wire is far more resistant to tangling or unraveling. Generally, any kind of wire can be used as a jumper cable or a wire for a circuit. For example, telephone cord or Teflon wire. Just make sure that the insulation is stripped off using a wire stripper, like this one here. Another thing to note is your wires should be insulated, meaning that all metal parts are covered in a layer. This prevents you from electrocuting or short-circuiting any components. The next component on our list is the resistor. The resistor is a fundamental part in all circuits as it provides resistance measured in ohms. Here we have a single resistor. As you can see, there are 4 colored bands on the resistor. In this case, brown, black, brown, and gold. These colors represent the resistor's color code, which also correlates to the resistor's value in ohms. I'll link a color code calculator in the description, which allows you to determine the amount of ohms each resistor has based on color code. This resistor, for example, is 100 ohms. And as you can see, different resistors have different ohms according to colors. An important tool when creating circuits is the breadboard. Breadboards come in all shapes and sizes, in this case a full-sized one. What breadboards allow you to do is to create circuits without using solder, which is extremely important when prototyping as you'll be rewiring your circuits again and again and again. So at this point, I'll put up a picture of what a breadboard looks inside, as it'll aid you in this description of a breadboard. So to use a breadboard, there are key pieces that you must remember. On the top and bottom, symbolized by the plus and minus signs, are power rails. As you can see in the diagram and in the inside picture, the power rails have metal pieces that run along the entire length of the breadboard. This means that whenever you put a jumper cable in it, it powers the entire rail. Now, on closer inspection, the main part of the breadboard looks like a grid, but not all of it is connected. As you can see, Metal runs downwards in columns. Power is delivered through these columns, meaning that column 1 is not connected to column 2, meaning the power is not transferred into column 2. In the center, we have a divider. This divider divides the board in half, dividing power rail and the main part of the board. An important feature of this groove is it allows support for integrated circuits or microprocessors, which we'll be covering in a later part of this video. When used correctly, a breadboard can allow your circuits to be more organized and have more modules on them. Breadboards allow you to add more jumper cables, wires, LEDs, speakers, and more, which allows you to make your circuits far more specialized. LEDs are one of the more simpler modules that you will use when making circuits. LEDs come in many different colors, for example green, red, and white, and each of them provides light. Keep in mind when using LEDs that the two metal barbs are different colors. The longer one is used for positive and the second one is negative. You would generally use a resistor when using an LED to prevent the LED from burning out. Speakers are another simple component in circuitry. As the name suggests, speakers are used to create sounds. Like the LED, the speaker has two barbs, though this time the barbs are of the same length. They serve the same purpose. One is positive and one is negative. It's just that you have to guess and check on which one is which. The best way to do so is to use a breadboard, as you can repeatedly use and flip the speaker until the correct configuration is reached. This is what the typical button looks like for a circuit. Buttons are used like switches, which are used to turn modules on a circuit on and off by controlling the flow of electricity. Let's take things one step further and introduce you to the concept of a microcontroller. So, microcontrollers are basically everywhere nowadays. And what they allow you to do is they allow you to add complexity to your circuitry. Now, what is a microcontroller? A microcontroller is basically a PCB with a processor and some memory on it. And what this allows you to do is it allows you to use code and translate it into circuitry by allowing you to power certain parts of the circuit using ports. Now you can see that there's a difference between these two microcontrollers. This one is a Genuino 101, and this one is an Adafruit Trinket. Now don't be fooled by their size. Microcontrollers come in all different shapes and sizes, but they do serve different purposes. For example, this Genuino 101 has a far more powerful processor and more memory than this Trinket. And this becomes extremely useful when you're dealing with a lot of calculations, as the stronger processor can allow you to run those calculations far faster. This can be used in projects like robots running on gyroscopes or accelerometers. Meanwhile, the Adafruit Trinket excels in smaller projects, for example, wristbands. Now you may have noticed something in particular with the Genuino 101 board. These black ports on the bottom here look awfully similar to the ports on a breadboard. And you wouldn't be wrong. These ports can also accept jumper cables, LEDs, and even speakers. But there's one key difference. If you look closely, each of these ports are labeled ground, 13, 12, 11, and etc. These are extremely important when it comes to coding with these boards, as these are the names of the ports that will be addressed in the code. For example, if you plugged in a jumper cable on pin 13, you would have to address pin 13 in the coding to send electricity to the jumper cable. Meanwhile, on the Trinket, it doesn't have the same ports as it does as the Genuino 1 does. Instead, it has pins. This makes it difficult to create projects with it without a breadboard, unless you have another source of input, for example, a male to female connector. Like all other electronics, microcontrollers need to be powered as well. Luckily, there are many ways to do so. One way is to use USB. Just keep in mind that different microcontrollers may need different kinds of USB. For example, the Genuino 101 uses Type B, and the Trinket uses mini USB. The reason why USB is such a popular way to power a board is because a USB is needed to code the board. By plugging in one side to the board and plugging the other side into a device, for example, a laptop or a desktop, you can upload code into the board. Another way, if your board allows it, is to use an AC to DC adapter. For example, the Genuino 101 board allows AC to DC. Just make sure that you have the right AC to DC adapter. Another way is to use external battery pack. By using external battery pack, it allows you to make your board mobile and not plugged into anything. Just make sure you have the code pre-uploaded into your board. So here are two boards that are powered using different methods. This Genuino 101 is being powered by an AC to DC adapter, this cord right here. And you can tell it's on because the power indicator is turned on. This Trinket, on the other hand, is being powered by a battery, as you can see here. The battery takes a little bit of circuitry, as you can see here, but generally speaking, it is very efficient and very useful. To set it up, all you need to do is find the ground cable, the ground port on the backpack, and connect it to the ground on the Trinket. And same thing for the BAT. And with that, the power indicator should be working. Once you plugged in your microcontroller, this is what it should look like. Look for a green power indicator and make sure it's turned on. Now, if we look towards the code, this is what the Arduino IDE looks like, version 1.8.0. This is what we're going to be using to program our board. This large white area here is where you'll fit your code. For the sake of this video, I will not be talking about how to code an Arduino, as that requires an entire video on its own. There are countless other tutorials on YouTube that you can check out for this. But what I'll do for this video is I'll briefly go over the certain aspects of this IDE. As I mentioned before, this white area is where you'll fit your code. This arrow button here is the upload button. Once you finish writing your code and plugged in your Arduino board, you can click the upload button to upload the sketch onto your Arduino where it will be saved. This black area here is the console. Once you upload, your console should output that your code has been successfully uploaded to your Arduino board. So as you can see here, it's pretty blank, and that's because it is. This is a completely new sketch. But luckily, Arduino supplies us with example sketches, for example, the blink method. This is what a fully fledged Arduino code should look like. And if I run it, it'll say compiling sketch, and a progress bar should appear. Once the progress bar is complete, it'll output that it has completed the sketch and has uploaded successfully to the board. Another key thing to look out for is that Arduino requires you to have the correct board selected for the Arduino project. To check this, you can go to Tools and then Board. Right now, I'm using the Arduino 101, which is why it's selected in the board menu. But as you can see, there are countless other boards. Make sure you select the correct one for your project. As an example, I'll show you two example sketches that can be found on the Arduino IDE. The first one is the blink method, as stated before. This is what the code looks like, which is pretty simple. At this point, I'll put up a picture of both the blueprint and the schematics for you to check out if you want to try this on your own. So if you use the exact same blueprint and code that I have, this is the outcome you should get. The LED on the breadboard should blink at the exact same time that the indicator LED on the Genuino 101 blinks at. So from the code, we can already tell that pin 13 will be used, as pin 13 is the default pin used in the blink sketch. So I powered it through here, and the red wire represents the power, and it goes to the resistor, as you can see on the blueprint, and it goes to the LED and then back into the ground, which goes into the ground port on the Arduino. This completes the circuit. And the program basically dictates when electricity is going to flow through port 13, triggering the light to flick. Here's what the console should look like on your IDE. A harder example would be the tone melody sketch. This is what it looks like. The reason why tone melody is a little bit harder than Blink is because it incorporates another method. Pitches.h automatically loads in with tone melody once you load it in from the example. Yet again, I'll put up a picture of the blueprint and a schematic of this code. This time we have the tone melody circuit, and if you followed the code and the blueprint as I showed you, this is what it should look like. So as you can see, it's not doing anything now, but what tone melody does is that it actually plays a little song. So we'll run this by clicking the upload button, and as you see in the console, it is now loading to the board. So we'll just wait for that to finish, and there it is. So now it's saying starting download script. And now what it should say is master reset. Now, master reset button comes in different parts of the board, depending on the board, but in this case, it's right here. So we'll click it, and it says success, and the sketch will execute in about 5 seconds. So listen closely. That was tone melody playing. Just one reminder, last time the default port was 13, this time the port is port 8. The reason why it is port 8 is because in the code, right here, no tone is labeled 8. Everything else is the same. The red wire goes from port 8 into the breadboard, which then follows into the speaker, which then goes through a resistor, this time it's 470 ohms, and then back into a white wire, which goes into ground, completing the circuit. In circuitry, you may hear new terms such as current, voltage, and resistance. What do each of those mean? Well, current is the flow of electricity, or electric charge within a conductive surface. Current is measured with amperes. Voltage, on the other hand, is the pressure supplied by a power source that moves current through the conductive loop. Voltage is measured in volts. Resistance is a little bit different. It is the limiting factor for current as it restricts current from moving. Think of it as a bottle, where the bottleneck is the resistance and the water within the bottle is the current. The bottleneck reduces the flow of current. Resistance is measured in ohms. Now, why am I bringing up voltage, current, and resistance? Well, these three variables are extremely important when creating schematics, which are the instructions to making safe circuits. To calculate for these three variables, we can use something called Ohm's law. Ohm's law can be simplified into a simple equation, I equals V over R. To make it even simpler, we can make it a visualization by putting all three variables into a triangle like this. By keeping this triangle around, you can easily figure out the values for I, V, and R in any component in any given circuit. It is especially useful when trying to figure out the resistance needed for a certain component. How it works is simple. Simply cover the variable that you're missing and use an operation with the following two variables to get the product, which is the unknown variable. An example of this is, for example, we don't know V. We can just cover up V, and as you can see, I times R equals V. Another way to do it is we can cover up R. In this case, V over I equals R. Speaking of schematics, there are two kinds of circuits you need to watch out for. The first one is series, which is defined as a power source being connected to all of its modules in line with the same connection. The connection can be anything, for example, a wire. Just make sure that all of the modules are on that wire and reconnect back with the power source. The second kind of circuit is called parallel. A parallel circuit is kind of like a series circuit, but instead, The modules are on wires that are parallel to each other and reconnect to the main wire that leads back to the power source. There is another important difference between these two styles of circuits, and that difference is the equations needed to calculate for total resistance, total current, and total voltage. These equations are extremely important as the total resistance, total current, and total voltage are the variables used in Ohm's law. Starting off with resistance, the total resistance within a series circuit is equal to the sum of all the resistance within the circuit, meaning that the total resistance is equal to the resistance of all the components combined in the circuit. On the other hand, in a parallel circuit, 1 over the total resistance is equal to 1 over the first resistance plus 1 over the second resistance plus 1 over the third resistance, and so on. To get the actual total resistance within a parallel circuit, you have to do a bit of algebra. Calculating for total current in both types of circuits are fairly easy. In a series circuit, the total current is always constant, as in the total current is equal to I1, which equals to I2, which equals to I3, and it doesn't change. In a parallel circuit, it's a little bit different. The way you calculate for total current is the same as how you would calculate for total resistance in a series circuit, as in the total current is equal to the current of the first component plus the second component plus the third component. Voltage is also pretty easy to calculate in both circuits. In series, total voltage is equal to the sum of all the voltages within the circuit. And in parallel, the total voltage is always constant. So moving on to the topic of schematics, we'll be using a program called Fritzing. And Fritzing is a very useful program because what we can do is we can visualize a schematic in multiple ways. We can use a breadboard, we can use an actual proper schematic, a PCB, and even the code used in Arduino. So to start out with this tutorial, I'll show you how to use the breadboard. And for this project, I'll be using a previous example that we used in the video, which was our speaker. And here is a finished product of what the speaker should look like. And here I'll go through the steps on how you can make the schematic for yourself. This schematic required us to use a microcontroller, and that microcontroller can be loaded up by using these tabs here. So here we can see the Arduino tab, and it just preloaded all of the boards Arduino has. And here we have a special part that you can download on a website, and basically in Arduino you won't be able to find the Arduino 101, so I downloaded a custom version of it, and I'll just import in this custom microcontroller. So now you can see we have the Arduino 101 next to our breadboard. So now we can go back to core, and core basically has all of the fundamental parts you'll need in a schematic. So using these parts, we can actually recreate a schematic. So as you saw before, we have to use our 8-port. And to create a wire that connects to your breadboard, all you need to do is simply click, hold, and drag. And we'll place it right here on the breadboard. And you'll see that there's a green connection showing that the entire row here on the breadboard is connected. So now simply we'll scroll down and find a piezo speaker, which is right here. And we'll drop that in. Now you see it's not connected because we don't want this speaker in this orientation because it'll block off what we can see. So we can simply rotate it. If you head to the corner of the speaker, just like in Photoshop, you can actually rotate the speaker. So now we have the speaker lined up, and we'll place it right here. Now you can see that another green line has formed, showing that the electricity flows through the speaker and into the next column. So with this, we will head on and add in a resistor, which we'll place right here. And you'll see that the resistor has its own color code, and you can actually fix this by using the inspector to decide. And we'll add it and change it to 470 ohms. And you can see that the color has changed. And then we can add in the ground, which we'll just plug in like this. So now we have a completed diagram, just like this one here. And keep in mind that when using multiple modules, for example, like an LED, a button, and a speaker, it may be more helpful to use the universal ground and power bars, as it will make it a lot more organized. So with this, we now can click the schematics tab, and you see that there's a schematic up here. we'll just scroll to it and zoom in. So here's our schematic. And all we need to do is click the auto route button, and it'll automatically create a routing system that makes the schematic all nice and neat. So now you can also save this file by clicking export and exporting it as an image to PNG or anything else, or you can even save the project file and share it to your friends. Okay, now that you have watched the entire video, you should be able to create your own circuits, and to test this, we'll create a button sketch and a button circuit to basically put everything all together. So first we have our breadboard here on Fritzing, and we'll just import a microcontroller. So here we have the Arduino 101, and now we just create our circuit diagram on this blueprint. So let's go back to core, and then we can just add in some wires. We'll use universal ground this time because we're using two modules, an LED and a button. So we'll hook up ground to here, and now you can see all of the ground. This entire row is powered with the ground. And now we add in one wire from the universal ground to the actual main part of the breadboard. Now we just put in an LED, and it will return back here. So what we need next is a resistor, and this resistor should be 100 ohms. And we'll go through these calculations by the end of this, and I'll show you how I got 100 ohms. Then we need a wire connecting back to port 13, because port 13 handles the LED. Next we need our button. We'll connect it here, right past the little dip here, and we'll add in another resistor right here, and we have to orientate this a little bit more because we have to fix this to the universal ground. We'll just stretch that out here, and now you can see they're both connected. Now we need two more wires, and then we're done the circuit. One wire will connect from the right side of the button and connect to the 5 volt, which will power the button. And then we need one more to connect the button to port 2, which controls the button. And now we have our blueprint here. Now we just head to schematics, and you see how there's a lot of red, but just like last time, we'll just auto route it, and it should give us a complete schematic. Okay, so let's go ahead and click auto route, and it'll start building its own path. So here we have a couple of red spots. No problem, we'll just fix that. There you go, and there we go. And now all we need to do is export them as JPEGs or PNGs, and we'll head out to the actual physical part of building a circuit. Now we just simply follow the schematics that we just created, and we put it all on a breadboard. So here you can see everything follows the schematic. We're using the universal ground again, and it connects to the light. There's a 100 ohm resistor, and it goes back to port 13. And then for the button, we have a wire that connects from port 2 into the button, and then it goes back into the 5 volt. And yet again, we have a 470 ohm resistor going to universal ground. So now we just simply plug this in to our laptop, and we run the Arduino code, which I'll show you in a second. Okay, so now you see that we plugged it in, and the LED is turned on, and we have the indicator LED on the board light lit up, which means that everything is powered. And here we have our button sketch, and I'll just click upload real quick. So now I'll begin uploading and compiling the sketch. Okay, so now it says press master reset, which we'll do right now. and it says sketch will execute in 5 seconds. So now the button has turned on since it's 5 seconds, and what should happen is that the LED should flicker when we press the button. As you can see, the LED gets brighter and dimmer as I press the button. So there you have it. There's a complete circuit based on what we learned on. So now, based on resistors, I'm going to show you how to get the proper values for the resistors. Okay, so this is personally how I calculate for voltage, current, and resistance, and sometimes even power. I use a website called Ohm's Law Calculator, and this is a really good calculator because it's really quick. It's better than writing it with pencil and paper, and it automatically fills in the blanks for this equation. So to get the 470 watts ohms that I used for my circuit, I inputted the voltage that we used for our circuit, which was 5 volts. And then for the LED is at 50 milliamps. So now we have two of the variables. All we need to do now is click calculate, and we instantly get 100 ohms. Now for the button, on the other hand, it was a bit different. The button still uses 5 volts, as the whole circuit was running on 5 volts, but this time the button was using 10 milliamps. And you can see that the ohms are 500, but a 500 ohm resistor is really hard to come by. So I just rounded it down to 470, and that wouldn't make that much of a difference. So I'll link this in the description so you can use it. It is a really useful website, and I'll also be linking the color code for resistors in the description as well. Thank you for watching this tutorial on circuitry. I hope you found it really helpful. In the description, I'll be putting links to the Fritzing website, along with the Ohm's Law calculator and the resistor color code, as well as the Arduino website, which has a huge forum where you can ask a lot of experts on how to code and how to do circuitry. So, thank you all for watching, and have a wonderful day.